Imagine a lock with two keyholes. You need both keys to open it. That's digenic inheritance, or DI. It's when two genes team up to control a single trait. This is different from what we usually see. We typically think one gene equals one trait. Digenic inheritance changes that. In typical inheritance, one gene is the boss. It determines if you have brown eyes or blue. DI is more complex. Two genes share the responsibility. Think of it like baking a cake. One gene might be flour. The other gene might be sugar. You need both for a sweet treat. DI is still a relatively new concept in genetics. We're just beginning to understand how it works, but it's already changing the way we think about inherited traits and diseases. What are the implications of this new understanding? How does it change our approach to medicine and treatment? Let's dive deeper into the world of digenic inheritance. There are two main types of DI: true DI and pseudo-DI. In true DI, both genes are equally important. Both are absolutely necessary for the trait to appear. Think back to our lock analogy. Both keys are essential. Pseudo-DI is a bit different. One gene plays the leading role. The second gene acts as a modifier. It can influence how strong the trait is. Imagine a dimmer switch. The main gene turns on the light. The modifier gene adjusts the brightness. Distinguishing between true DI and pseudo-DI can be tricky. It often requires sophisticated genetic testing. Why is this distinction so important? Because understanding the interplay of genes in both types of DI is crucial for diagnosis and treatment. Let's delve into some specific examples to illustrate how true DI manifests in real-world diseases. Several diseases are linked to true DI. One example is Bardet-Biedl syndrome. It's a rare disorder affecting many parts of the body. Vision, limbs, and even organ development can be impacted. Individuals with Bardet-Biedl syndrome often experience a range of symptoms. Another example is retinitis pigmentosa. This disease causes vision loss. It primarily affects the retina, the light-sensitive tissue at the back of the eye. Over time, individuals with retinitis pigmentosa experience a gradual decline in their vision. These diseases highlight the complexity of DI. They demonstrate how two genes can interact to cause significant health problems. But how do we differentiate these diseases from those influenced by genetic modifiers? Let's shed some light on the role of these modifiers. Genetic modifiers add another layer of complexity to inheritance. They don't cause the disease themselves. Instead, they influence how a disease expresses itself. Think of it like this. A modifier gene might make a disease more severe, or it could cause it to appear earlier in life. Cystic fibrosis, or CF, is a good example of a disease influenced by genetic modifiers. CF is a genetic disorder that affects the lungs and digestive system. While a single gene is primarily responsible for CF, other genes can modify the severity of the disease. These modifiers help explain why some people with CF have mild symptoms. Others experience more severe complications. Understanding the role of modifiers is crucial for developing personalized treatments. But how do we identify these genetic modifiers in the vast landscape of our DNA? Section 5, Sequencing the Future, High-Throughput Technology and Digenic Discovery. Identifying DI genes used to be like finding a needle in a haystack. It was a slow and laborious process. Now we have high-throughput sequencing. This technology allows us to analyze massive amounts of DNA quickly and efficiently. Think of it like searching for a specific book in a library. In the past, we had to search shelf by shelf. Now, we have a search engine that can scan the entire library in seconds. High-throughput sequencing is revolutionizing our understanding of DI. This technology is helping us identify more DI genes. It's also revealing the complex interactions between genes in both health and disease. This knowledge is paving the way for more precise and effective treatments. How is this knowledge being translated into tangible medical advancements? Let's explore the impact of digenic inheritance on the field of precision medicine. Section 6, Precision Medicine, Tailoring Treatments with Digenic Insights. Precision medicine is about tailoring treatments to individual patients. DI plays a crucial role in this approach. By understanding a patient's unique genetic makeup, doctors can make more informed decisions about their care. For example, knowing a patient has a specific DI gene mutation could guide drug selection. It could also help doctors predict a patient's risk of developing certain diseases. This personalized approach is more effective than traditional one-size-fits-all medicine. DI is still a relatively new area of research, but it holds enormous potential for precision medicine. As we learn more about DI, we can develop even more targeted and effective treatments. Digenic inheritance represents a paradigm shift in our understanding of genetics. It challenges the traditional one-gene, one-trait model. It highlights the intricate interplay of genes in shaping our health. Section 7. The future of digenic research. Unraveling complexity in the code of life. The future of DI research is full of promise. As technology advances, we'll be able to study DI in even greater detail. This will lead to a deeper understanding of the genetic basis of complex diseases. Imagine a world where we can predict a person's risk of developing a disease based on their DI profile. Imagine developing treatments that target the specific genes involved in a disease. This is the future that DI research is building. The journey into the world of digenic inheritance has just begun. We are only scratching the surface of its complexity and implications. Yet, the potential rewards are vast. Digenic inheritance is not just a scientific curiosity. It's a fundamental principle of genetics with profound implications for human health. Section 8. Digenic inheritance, a new frontier in genetics. Digenic inheritance is revolutionizing our understanding of genetics. It challenges the traditional Mendelian view of inheritance, where one gene dictates one trait. DI reveals a more complex picture, where genes interact and collaborate to shape our characteristics. This new understanding has profound implications for our approach to medicine and treatment. It paves the way for personalized medicine, where treatments are tailored to an individual's unique genetic makeup. The future of medicine lies in unraveling the complexities of our genetic code. Digenic inheritance is a key to unlocking this code. It offers a glimpse into the intricate world of gene interactions and their impact on human health. The more we learn about DI, the better equipped we'll be to diagnose, treat, and even prevent diseases. The future of medicine is personalized, predictive, and preventive. Digenic inheritance is a crucial piece of the puzzle in achieving this vision. Section 9. The implications for personalized medicine. Digenic inheritance is a game changer for personalized medicine. It allows us to move beyond the one-size-fits-all approach to treatment. By understanding a patient's unique DI profile, we can tailor treatments to their specific needs. Imagine a future where we can predict a person's risk of developing a disease based on their DI profile. Imagine developing gene therapies that target the specific genes involved in a disease. This is the potential of digenic inheritance for personalized medicine. The knowledge gained from DI research will lead to more effective treatments with fewer side effects. It will empower individuals to take control of their health and make informed decisions about their care. Digenic inheritance is ushering in a new era of personalized medicine, where treatments are as unique as the individuals they are designed to help. Section 10. Beyond the double helix, the future of genetic exploration. The discovery of digenic inheritance is just the tip of the iceberg. It opens up a whole new world of genetic exploration. We are only beginning to scratch the surface of gene interactions and their impact on human health. The future holds exciting possibilities. Imagine discovering new forms of inheritance, even more complex than DI. Imagine developing technologies that allow us to edit our genes and correct genetic defects. The journey into the world of genetics is far from over. Digenic inheritance is a signpost, pointing us towards a future of discovery and innovation. It's a future where we can unlock the secrets of our genetic code and use that knowledge to improve human health. The future of genetics is bright, and digenic inheritance is lighting the way.